like test it and see if it's
I don't think
Okay, I'm gonna go ahead and go live here. So we
Can you hear me?
Okay, yeah, you are on. I just heard you. Yeah.
Good to go.
Okay.
I think we're good. If you wanna, you can shut down your face, then we can feel good. And
Yeah.
you can just text if there's any issues.
Sounds great. Thanks, Pete.
Great, thanks so much, Christy.
You're welcome. Feel better.
When you're done, you can, when it's all done, you can just hit stop recording and then stop live streaming, and it'll ask you if you want to just correct it later. And I usually don't. I just let it finish, and then eventually it'll stop on my end. And there you go.
Got it. Okay.
Awesome.
Thanks.
Thanks.
Bye.
I think a lot of times would be
We're good at that. Not really.
That's right.
Right on time.
Just like
In the nick of
Catholics.
time.
Just like Catholics for coffee and donuts. They're always there right on time.
Yep.
Never early.
Yep.
Oh, I thought you were like not trying to.
A pointer? Yeah, there is a.
Yeah, I know I'm over it.
Do you know where the laser pointer is kept? Oh, I think this is.
There's a long,
Is it this little guy? right
no,
here?
there's a better one. There's a one that yeah, because I don't ever use it. Oh, wait a minute. It's this.
Yeah.
Does it work?
Wait.
That one doesn't work.
That one doesn't work. Maybe it's on.
Yeah,
Yeah,
there it
we
is.
go.
That one's really
Great. It's one of those things. All right, everyone, let's go ahead and get started. So it is my pleasure to introduce our colloquium speaker today, Dr. Akshaya Nikumbh, who is a postdoctoral fellow at GFDL and also Princeton University. So Akshaya obtained her PhD from the Indian Institute of Science, and a lot of her work has revolved around understanding extreme precipitation and extreme rainfall. So a lot of her PhD work was looking at understanding the mechanisms behind these extreme precipitation events in India. And now she's doing a lot of work to try to understand to understand the role of, for example, resolution on capturing, model resolution on capturing extreme precipitation within the GFDL model. And she also has a lot of interest in tropical-extratropical interactions. So we've chatted quite a bit about that. So without further ado, go ahead and take it away. Thank you.
Thank you for nice introduction, Stephanie. So it's a pleasure to be here. I have been visiting this department since last 1 year. I hope I'm audible. Okay. So yeah, so I have had great pleasure to interact with many of you over this past year. And I would like to thank Ankur for providing me lab space whenever needed. So it's been nice, and I hope to interact with all of you. I'll be here for next 10 more days, so it will be nice to interact with you. Please feel free to stop by my office whenever you feel like. I'll be happy to chat more. So getting back to today's talk, I have worked on heavy rainfall events, as Stephanie mentioned. I'll discuss how these heavy rainfall events of different spatial extent are triggered over India. Let's get into talk. So this is overview of my talk. I briefly introduce studies on heavy rainfall events over India and in general about precipitation extremes. Then I'll show how including size of event gives different perspective of their observed trends and also underlying physical processes. We'll see how these large-scale heavy rainfall events are triggered and mechanism for different spatial extent of heavy rainfall events over central India. Finally, if I get time, I'll briefly touch upon how do we understand their observed trends and summarize my results. So we know studying heavy rainfall events is important because they trigger flood. But other than that, they're important because they can change spatial temporal distribution of rainfall. So there is some evidence by this study, which is Karamkar et al., where they looked at heavy rainfall events during break phase of monsoon. So when we get less rainfall over central India, that is called break phase. Heavy rainfall events during that phase can affect initiation of next active phase and also the intensity. So there is some evidence that these events can modify spatial temporal distribution of the rainfall for India that is shown. These events, they are difficult to predict. So one of the major challenges in front of today's weather model is to predict the location, accurate location and intensity of heavy rainfall event. And third, there is large uncertainty in their future prediction, especially over tropics. So there are certain models which predict almost no change in extreme rainfall events. On the other hand, there are other models that predict more than 30% change. So there is large uncertainty in future prediction of heavy rainfall events, especially over tropics. So these are studies where early 2000, there are many studies they had reported there is observed rising trend in heavy rainfall events. So here extreme means heavy rainfall events, so I'm talking about upper percentile of events. So it has been increasing and various hypotheses have tried to explain that. So initial studies like Ajay Mohan et al., their hypothesis was like synoptic activity has been increasing over central India. So monsoon low pressure system that trigger these heavy rainfall events, they are increasing and they possibly explain the rising trend. However, recent studies show that it is moisture flux from Arabian Sea that brings moisture from Arabian Sea to central India that has been changing and that possibly explains the observed trend. So there isn't consensus among different studies what leads to changes in precipitation extents over central India and why they are increasing. If we look at like literature on precipitation extremes, early 90s studies had reported that with global warming or with rising temperature, there would be increase in precipitation extremes. So simple hypothesis or thermodynamic way of explaining this is that since in warmer atmosphere, there would be more moisture in the atmosphere using Clapeyron equation and precipitating system that form in such a moist environment would rain out or precipitate out at higher rain rate. So that's how we should expect like more extreme rainfall events in warming world. And like as I mentioned, like in early 2000 over India it was reported that indeed these precipitation extremes are increasing and over world also like so this is like one very interesting aspect of climate studies where studies which had reported in theory that there would be rise in precipitation extremes and within a decade you could report it with observation that indeed these precipitation extremes are increasing. And in terms of like hypothesis on why or how precipitation extremes should change, there are these thermodynamic ways of explaining that I mentioned, but there are also changes in circulation. So as we call it dynamic changes, so changes related to circulation can either offset these thermodynamic changes or they can either amplify precipitation extremes, especially over South Asia that has been shown to be a possibility. On the other hand, they can also like dampen down the changes due to thermodynamics. So changes due to dynamics have large uncertainty. And over tropics, these are the changes that adds to uncertainty in their future projection. So much of this literature, it revolves around the intensity of precipitation extremes. So when we say extreme rainfall event, it has different characteristics like its intensity, its size and duration. So intensity, there is a lot of literature. For duration, it has been shown or suggested that the events would be of smaller duration, so they would occur over less time scale as compared to current weather extremes. But there isn't much literature on spatial aggregation. So whether size of events has already been changing or what determines the spatial extent of extreme rainfall events. So these are the questions that I had when I started my PhD, and I'm still pursuing it. Today I'm just going to show part of it for Central India, how it is important to consider spatial extent of heavy rainfall events. Another motivation is when I looked at these different high impact heavy rainfall events over India, events like Mumbai or like so top panel here shows events which were like smaller in size. On the other hand, bottom panel shows these events like Uttarakhand or Gujarat. Gujarat like event occupied almost like entire state. So these events are of different spatial temporal scale. So question here is like how similar or different extreme rainfall events of different spatial scales are. So I'll talk about mainly central India, but there are some interesting contrasts, some similarities and differences in events of different spatial extents are. Over India, another major issue has been this widespread extreme rainfall events. So these are like 4 consecutive monsoon years where we receive this widespread flooding due to large-scale extreme rainfall events. And in today's talk, I'll also show that over central India, these large-scale events are increasing, and I'll also discuss mechanism for them. So let's start with what is an extreme rainfall event. So if rainfall exceeds certain threshold, like fixed threshold, or it could be percentile threshold, then we call that is an extreme rainfall event. So this particular study by Goswami et al. They looked at central India. So shading here indicates climatology of rainfall. So this is like homogeneous region where most studies over India have reported that there is rising precipitation extremes. The way this study has defined extreme is like whenever rainfall exceeds 150 mm per day, all such number of grids over central India during monsoon, and this is time series of that count. So here we can see there is rising number of extremes. So this seems like a reasonable conclusion that frequency of heavy rainfall events is increasing over central India, but there is catch, and that catch is this. So if you have event like this, so this is like one heavy rainfall event, extreme rainfall event. Here we can see this one single event is occupying multiple grids. So in this case, it occupies like 7 different grids. So if we just count number of grids that experience extreme rainfall without considering their spatial co-location, there is possibility that this will be overestimated. So instead of this one single event, it will be counted as 7 different events. So in my work, I use like same data set as earlier study I had used. So it is 1 degree by 1 degree Indian Meteorological Department data, same study region as central India. And here I'll be showing results from 99.5 percentile threshold. I have also done it for constant threshold like 150 mm per day that earlier study I had used. To identify size, I use this image processing algorithm called connected component algorithm. So it can extract features like here, suppose this event occupied 7 grids. So size of this event is number of grids occupied by that event. So here size is 7 here. So based on size, then I classify these events as small, medium, or large. Small events are isolated events that occupy just 1 grid. Medium events have size 2 to 5, and large events have size 6. So this is an example of large event. So now let's look at impact of size in their observed trend. To do that, I have defined these different quantities. So NT here is number of grids that experience extreme rainfall in entire season. So earlier studies had shown reported this quantity. So they had shown time series for NT. Since I'm considering size of these events, and size is in terms of like grid units, so if I take size of events over their number of occurrence, which is any here, I should get NT. So here this is like time series for 3 different quantities. And also I can define average size of events in a season, which is NT by N. So NE is number of events, NT is number of grids that experience extreme rainfall in entire monsoon season. So here black line indicates NT, or time series of NT. So it is smooth time series. Then NE is number of events. So here we can see how number of events are changing. And then brown line indicates average size of events. So here dotted line indicates average size from 1951 to 1980. So here we can see, as reported in earlier studies, NT has been constantly increasing, but not the number of events. So here we can see till 1990 number of events were increasing, but after 1990 they are actually decreasing. So this recent increase in heavy rainfall events over central India, it is not coming from their number of occurrences, but it is coming from their average size. So there are maybe less number of events, but they are of larger spatial extent. So this indicates that this, what earlier studies had reported, that frequency has been rising. That might not be exactly correct statement. It is so there are like interannual variation in the frequency of occurrence of these events, but this trend is coming after 1990 from the spatial aggregation rather than the frequency of occurrence. So we can look at further like how these changes in size and changes in number of occurrences contributed to changes in NT. So I have divided entire study period into 5 equal intervals, and this is a fractional change. So gray bar here indicates fractional change in NT, orange indicates fractional change in size, and blue indicates fractional change in number. So here we can see in first two intervals, change in NT was mainly coming from changes in number of occurrence. On the other hand, in last two intervals, change is mainly coming from the size. So basically, same conclusion that recent years, number of events are actually decreasing, but their spatial extent is increasing, or events of larger size, they are increasing. So what is typical size of heavy rainfall events over central India? So here on left side I have shown probability distribution for two different time periods. So I have divided entire study period into two halves, two equal halves. So here we can see x-axis here is size, y-axis is probability, and blue color indicates first half of study period, and orange indicates the recent half. So here we can see mostly these events are of smaller size, so more than 90% of these events have size 1. As you go towards like x-axis, the size of the probability of getting larger size event is pretty low, but this probability has increased in second half. So there were some very large size events like size 11 and 13. They were not reported in earlier half of study period. So this shows that probability of getting larger size events has been increasing. We can also show that using a lot of different ways, but here one more way I'll show. So it is cumulative distribution function, so CDF. So contribution to CDF by different sizes, again two halves. So here we can see black indicates first half of study period. Here contribution to NT by size greater than 5 was almost null, which has increased more than 10% in the second half. Now let's get into what is the temporal and spatial distribution of this event. So x-axis here is year, y-axis is size, and shading indicates their count. So here we can see these events, small size events, they occurred most frequently between 1980s to 2000, but they are actually decreasing after 2001. On the other hand, medium size events, they are becoming more frequent after 1990. And most interesting part is this large size event, which have size greater than 6. So there were just 2 large size events before 1980, and they are becoming more frequent in recent years. So most of them have occurred after mid-80s, and most after 2000. And here we can see, so if we look at like trend in these events, which I have not shown here, for large event and medium event, there is a significant increasing trend, but it is not so for small event. So where do these events occur? So I have shown that using spatial distribution. So this is like normalized, also normalized by their maximum value for small, medium, and large. So we can see these small events, they occur mainly over western parts or over northern parts of central India. Medium events, they occur over central India, and large events have this very strong preference over central India. So they mainly occur here over the zonal band between 15 to 25 north, and they have this strong regional preference. And all of this is for monsoon season. So here, though in this particular plot I have shown you like entire India map, but for analysis I have used just central India that I had shown earlier. So now what triggers these events? So earlier studies I had shown that monsoon low pressure system triggers heavy rainfall events. So that I wanted to confirm. So I use this data set by Hardy and Bruce. So they use era interim data set to track vorticity maximum to identify this low pressure system. So monsoon low pressure system, most of them, they form over Bay of Bengal and move northwestward. So here this is track of one low pressure system, and shading here is rainfall. So this is example of like one extreme rainfall event that was triggered by this low pressure system. So I use this data set to look at like how these 3 different classes were associated with monsoon low pressure system. So for a small event, so for each event, I look on that particular day whether low pressure system had passed. If it had passed to central India, then I call it like it was associated with monsoon low. So 86% of small events were associated with monsoon lows. 92% of medium, and all of the large events were associated with monsoon lows. So it shows that over central India, the main physical mechanism for these events is monsoon low pressure system. Now this is spatial distribution of these different heavy rainfall events with respect to monsoon low. So center of this plot indicates location of low pressure system, and bubble indicates like 3 different classes. So here we can see large events, they are triggered very close to center of low pressure system and within like 500 kilometers, and mainly in southwestern sector. Small and medium events, they can occur slightly far, but still in western sector. So overall there is this western sector preference for these heavy rainfall events. I'll also discuss in a bit why it should be the case. So we see these heavy rainfall events, they are mainly associated with monsoon lows, and they occur mainly in the western sector. So then how these things are, how these 3 different classes are different. So that we can see using this surface pressure anomalies here. So here I have shown it for large, medium and small event. Day -7 indicates 7 days before event, and day 0 is day when extreme rainfall event occurred. So here we can see for large event there are these planetary scale anomalies which are not present for medium or small event. So there is still this monsoon trough kind of anomalies for medium and large event, but not so much for small event. So even though these events are mainly triggered by low pressure system, what this plot indicates that they might have like different large scale conditions. So I'll talk about this in a bit, more about it in a bit. But like from these observations that I had reported in first part, main conclusions to take out are like after 1990, it is size of heavy rainfall events that explain their rising trend, not the frequency of occurrence. Medium and large events, they are becoming more frequent over central India in recent decades. Then these extreme rainfall events of different spatial extent, they show distinct geographical preference. They are mainly associated with monsoon low pressure system, but have different large scale condition. So now, what triggers this large scale extreme rainfall event that we see here? So this I had shown you before. This is normalized count for large scale event. So they occur most frequently over this band of central India. Here I have overlaid this plot with climatological geopotential height. So here we can see 2 minimas in climatological geopotential height at 500 HPA. So this minima, this corresponds to location where monsoon low pressure systems come inland. So I had earlier shown you path of low pressure system that they form over bay and come inland. So this is the location where it comes most frequently. On the other hand, this is the location where you see mid-tropospheric cyclones. So these are another synoptic systems that form during monsoon. So we can see these events, they occur mainly over the location where synoptic systems occur most frequently during monsoon. Also, I had shown you like low pressure, large scale events, they are mainly associated with monsoon lows. So what is special about these monsoon lows that trigger this large scale extreme rainfall event? So my first case was maybe these are the low pressure system, they are the strongest and rarest. So maybe they are becoming most frequent in recent years and that trigger this large event, but that doesn't turn out to be the case. So I have taken this low pressure system data set, divided it into 2 classes. So LPS-LG is class of low pressure system that triggered large scale extreme rainfall event, and this is other class which had like strong low pressure system but did not trigger like a large scale extreme rainfall event. And this is box plot for vorticity at 850 HPA. So here we can see this vorticity wasn't much different, maybe slightly stronger for LPS-LG. But there were like much more stronger low pressure system that did not trigger like large scale extreme rainfall event. So clearly it is not just strength that determines large scale extreme rainfall event, but there is something more. And that turns out to be this secondary cyclonic vortex. So these are like 3 different examples of large scale extreme rainfall events. And here we can see like first column is relative vorticity in shading and winds at 850 HPA, so at low level. Second column shows same thing at mid level, and third column is rainfall. So like let's just pick out this one case. So this is like large scale extreme rainfall event triggered over here. We can see this event was triggered in the southwestern sector of this main low pressure system, but this system was not alone. It was assisted by this another cyclonic system. and it was also a synoptic system. So it is true for like all the large scale events that occurred during the study period and over that study region. That there were like two synoptic scale systems, and mainly this event was triggered in the southwestern sector of main low pressure system, but this other system was in its western sector, so west side of the main low pressure system. And we will see how this western side of another cyclonic vortex helps in the formation of large-scale extreme rainfall event. That happens because like for these events, main moisture source is Arabian Sea. So during monsoon we have this low-level jet that transfers moisture from Arabian Sea to inland over central India. So if you have like another cyclonic system that can enhance this moisture transport from Arabian Sea, so you get like these events which have like more moisture transport due to the secondary cyclonic vortex. There are other things also, so we can look at more into details of how secondary cyclonic vortex would help in formation of large event. So here I have shown composite geopotential anomalies in first panel. So here it shows since 2 days before and day 0 is day of extreme. So here we can see there are two locations of low in geopotential. So this is associated with monsoon low pressure system, and other low is secondary cyclonic vortex. So these two circulations merge at mid-troposphere. So this is at 500 HPA and intensifies. So in like mesoscale convective system literature or MCS literature, you might have heard about MCV or mid-tropospheric cyclonic vortex. That helps in organization of convection. So if you have like scattered convection, that can be organized better if you have like mid-tropospheric cyclonic vortex. So we can see in individual cases also that there are these mid-tropospheric cyclonic vortex condition in many cases that can help in organization of convection, and thereby you get this larger size event. Second panel here indicates pressure velocity. So it is averaged from 15 knot to 25 knot. So it is like longitude versus height plot. So here we can see there is this ascending region associated, strong ascending region associated with monsoon low pressure system, and also with secondary cyclonic vortex, which is more clear on day -1 and day 0. Both of these ascending zones, they merge, and this merging can also host large scale system. So here I've shown wind convergence in the bottom panel. So here blue color indicates convergence of wind and wind at 850 HPA. So here if you could see, this is like low pressure system, and there is a secondary cyclonic vortex. So in between these two cyclonic systems, there is like strong convergence zone which intensifies on day 0. So this strong organized convergence zone can host vertical velocity or ascending motion, which is also large scale and organized, and that can trigger this large scale extreme rainfall event. I also had mentioned like most of these extreme rainfall events, they occur in the western sector of monsoon low pressure system, so that we can understand during using this schematic. So like during monsoon we have warm continent and cold ocean, so there is reversal of temperature gradient. So whenever there is synoptic system that forms in such a setting, on eastern side you can imagine cold air going down because warm air will stay up. On the other hand, on the western side or western sector, warm air would rise up over like cold air. So there should be ascent in the western sector of this system. So this comes from the reversal of temperature gradient during monsoon because land is warmer than the ocean. You can also understand this using QG equation. So ascent should occur down shear of vortex gradient. So you have maximum vorticity here and you have easterly shear. So you should get ascent in the western sector. So that explains why you should get more extremes in the western sector of this monsoon low pressure system. You can also understand that using a positive tropic equation. So this is QG equation, John's favorite topic. So you can talk much better about it. So here, omega and Laplacian operator on omega and convergence of Q vector. So if this quantity is positive, that means there is ascending motion. So here we can break down it like this. So this quantity, it is modified for tropics by Pilates. So here looked at African easterly waves, and he cleverly changed this geostrophic wind or geostrophic stream function by just stream functions. So for tropics, we don't need to assume geostrophic balance. You can just look at like stream function and talk about like synoptic systems. So using this modified Q vector, we can use this equation even for monsoon low pressure system. And it seems to be doing like pretty good job. So here, this plot shows difference between this quantity, magnitude of Q vector for LPS LT minus LPS no LT. So center of that plot indicates location of low pressure system. And you can see in western sector there is generally ascent. So even though these two classes, LPS LT and LPS no LT, did not have much difference in their strength of vorticity, but you can see at mid-level there is more ascending motion or more dynamic forcing for this low pressure system that triggered large scale event. That would also come from this ascending motion because there is convergence between these two systems, so there is more dynamic forcing that is enhanced due to like the secondary cyclonic vortex. We can also look at thermodynamics during these events. So this is again vertical cross section. So this is like central India continent. Here indicate that height and longitude plot. Top panel here is anomalies in blood vessel frequency. These are like so dry static instability. So here we can see that there was this center associated with secondary cyclonic vortex and also convection over central India. On day 0, so atmosphere was highly convectively unstable. So that can explain thermodynamics during this event that can host then convective systems. Since these are like dry anomalies, we can look at the role of moisture by looking at these two quantities like theta and theta E. So theta is potential temperature and theta is equivalent potential temperature. So difference between these two profiles would indicate presence of moisture. So here I have done it at the location of this extreme rainfall event. So here we can see this is again height versus anomaly. So so it is profile of theta and theta E at the location of extreme rainfall event. So here we can see there was deep moisture influx for these events, which kind of went till upper troposphere on day -1, and on day 0 there was a lot of moisture. So there was deep moisture influx during such event, and that is enhanced by secondary cyclonic vortex. So earlier I had mentioned that the main moisture source for this system is Arabian Sea. So here these are like two plots for moisture convergence. So shading here is moisture convergence and vectors are moisture transport for LPS LT and LPS no LT. This is continent, it is hard to see, but this is Indian continent, and you can see it more clear over here. So this is like west coast, this is east coast and west coast. So here you can see this convergence. It comes from the fact that monsoon low pressure system, it interacts with this low level shape that transports moisture. So you see that one convergence zone over here, and this other convergence zone, it comes from secondary cyclonic vortex. So this plot shows more clearly how moisture transport is enhanced in the presence of secondary cyclonic vortex. In this class for LPS no LT, since there is no secondary cyclonic vortex, there is limited moisture transport. So this system's secondary cyclonic vortex can help in moisture transport as well. Other way it would help is like by slowing down propagation of this low pressure system. So monsoon lows, they mainly form over plate and come inland. So they propagate northwestward. If there is another synoptic-scale system, it can hinder its westward propagation. So here we have like a signal where this class of LPS LT, they tend to be slightly slower than the other class. So when I initially looked at this large-scale heavy rainfall event, I would see the indication of extratropical influence, but I wasn't sure about like how it works, because during monsoon we have strong easterly jet over India, and in tropical wave literature, if you see when these waves can come over tropics, they generally come over like westerly pockets, not over easterly region. So I was confused for some time. So during PhD, I kind of revisited this, during postdoc I revisited this topic because I came across ray tracing for two-dimensional flow where meridional wind velocity is not considered 0. So for that flow, I have done Rossby wave tracing, where here I had put like Rossby wave sources all over North Atlantic and trace these rays. So blue line indicates Rossby ray paths, and here filtered or shown only those rays that can come over India. So so shading here indicates meridional wind, and this contours zonal wind. So at actually metroposphere, you still have like westerly wind over India. So these waves almost follow like great circle path, and they can come over India within 2 weeks. So here, these markers, black markers indicates 5 days after integration, and orange indicates like 15 days. So within 2 weeks, Rossby rays that are generated in like Atlantic, they can follow this great circle path and come over India. Do you have like any doubt with this? Because this is like pretty complicated figures. If something is not clear, please feel free to ask and stop me in between. So like main conclusion here is that Rossby waves during summer monsoon, they still can come over India, but they come over at mid-troposphere, not at upper layer. So here I'll show for the same plot for 200 HPA. So here we can see these Rossby ray paths, they tend to follow like jet stream. During July and August, which are like peak monsoon months, they can come over India following by recurving near East Asia. So here we can see they can come, but they have like totally different pathways. On the other hand, if you look at like 500 HPA, they follow almost great circle path and come over India. So one hint I got, so even though Rossby ray tracing is like highly idealized way of looking at Rossby ray paths, they should not, or they may not follow like the real atmosphere, because you have this all complicated synoptic-scale interaction going on. But it gives at least idea about where I should look for a signal, and that I'll also talk in a bit. So this is like geopotential height anomalies at 200 HPA called large-scale extreme rainfall event. Day 0 is day when extreme rainfall occurs, 7 days before event. So in this plot, this data anomalies, they indicate the blocking high, almost like a blocking high over Atlantic. It was almost stationary, we can see here. So this is one important feature to look for this large event. And then other important is this Central Asian high. So I'll also show it in a bit. So these two important features you see during large-scale extreme rainfall event at upper level. If you look at the same plot at mid-level, now you start seeing tropical features too. So blocking high is much stronger. Here you can see. And here, this is like monsoon trough. So this is where India is. So these events, or secondary cyclonic vortex or monsoon low pressure system, they are embedded in this monsoon trough. And they are also like in phase with this Central Asian high. So if you have this Rossby wave pattern, so this Atlantic blocking high can trigger Rossby wave Lego response that we see on day -1 and day 0, and strengthen this Central Asian high, which is a feature which is generated due to this, and it is separate from Tibetan anticyclone. So during monsoon, there is Tibetan anticyclone, which is indication of like stronger the Tibetan anticyclone, it is stronger the monsoon. But if you have this feature of Central Asian high that is coming in phase with monsoon trough, that can help in formation of large events. That also I'll discuss. So right now I'm just showing you all the observation. I'll come to mechanism in a bit. So there is one more feature that I observe is like wave breaking. So in this case, I have shown like one example of large-scale extreme rainfall event. So star indicates location of that event. Shading indicates potential vorticity at 350 Kelvin, and contours indicate like geopotential height anomalies at 200 HPA. So I have plotted just positive anomalies to look at the location of Central Asian high. So this is Central Asian high, and you can see this potential vorticity. It is so PV streamers, they are coming towards equator in the eastern sector of the Central Asian high. So it's almost like Atlantic blocking high studies. They have noted that wave breaking occurs in the eastern edge, where these PV anomalies can be pushed towards tropics if you have this Central Asian high. So here we can see this like PV streamer, and then also cutoff high. So this event was triggered in the eastern edge of this PV streamer. So once you have this PV streamer, on its eastern side you get static instability and dynamic forcing that can help this large event. So here we can understand what I had shown earlier using this schematic. So in general, typical boreal monsoon condition, you have Tibetan anticyclone. westerly flow or westerly jet comes in and it gets deflected northward. So high PV air would usually get deflected northward if there is no centralization high. But if you have the centralization high, which is triggered as a Rossby response by Atlantic blocking high, it creates a path for it for high PV air to come towards equator. So here you can see this circulation, clockwise circulation associated with centralization high can push high PV air towards equator, and that's what we see here and leads to wave breaking. So here we can see this high PV air was pushed towards equator due to the centralization high. So that's how centralization high is important when you look at tropical-extratropical interaction. Because in presence of just Tibetan anticyclone, it would go actually northward. So that is also reason, like during summer monsoon, you don't see that much wave breaking, but in conditions like this, you would see wave breaking too. Yeah, sure.
Is that second panel meant to indicate that the Tibetan anticyclone goes through periods of weakening before the wave break upstream?
Weakening of.
Does the wave break to the east of or over Pakistan happen when the Tibetan anticyclone is weak? Do you need that to be a condition too?
That is something.
Because otherwise, it seems hard for anything to find its way equatorward in that.
Yeah. So okay, I get it now, right? So this Central Asian high has to be strong enough, and it has to be separated from Tibetan anticyclone, which is slightly pushed eastward than its usual location. So like here you can see that there is Tibetan anticyclone, but it is not at its usual location. There is this Central Asian high that tends to dominate. So you are right, if Tibetan anticyclone is strong enough, it wouldn't let this high PV air.
And if it's at the right latitude, as you just said, maybe it gets displaced a little bit?
Yeah, it gets displaced
Okay.
also. So that is the role of Central Asian high. Now we can understand this tropical-extratropical interaction using wave activity flux. So I have used Akshaya and Nikumbh formulation here, and it is stationary formulation, so stationary wave activity flux I will look at that. It is conserved under adiabatic and frictional conditions, so we can track these extratropical waves because the direction of this wave activity flux is parallel to group velocity too. So this is composite wave activity flux at 500 HPA for all large events, so from day 0 to day -7. And this is India over here. We can see over western part of India, this wave activity flux, it starts intruding. It is the location where you see this rays to come over India too. So at mid-level, you can see these are the locations where extratropical waves can come. So even though ray tracing was like calculation using idealized condition, it gave me a lot of interesting insights in understanding this large-scale extreme rainfall event. So for these events at mid-troposphere, you can see the wave activity flux that is intruding towards India. On the other hand, if I look at like upper level, it doesn't intrude. So this is like wave activity flux at down upper level at 200 HPA, 7 days before and day 0. So here you can see like over northwest India, it doesn't really come that much southward. So if I try to look for a signal at upper level, I don't get much signal for tropical-extratropical interaction during monsoon season. And but we can understand one interesting thing from this plot is that Atlantic blocking high, as I mentioned, it can trigger Rossby wave response. And to understand that, I have taken 2 boxes here. And also I mentioned Central Asian high can lead to wave breaking in its eastern edge. So I can understand that using wave activity flux. So I have taken these 2 boxes over here and plotted the divergence of wave activity flux. So divergence of wave activity flux, if it is positive, it would indicate it is wave source. On the other hand, if it is negative, it would indicate wave is breaking. So next to Atlantic blocking high, the box here, this box here we can see wave activity flux was positive. That means conditions were conducive for like Rossby wave formation. So it is wave source. On the other hand, Central Asian high, you can see the negative values in wave activity convergence. So that means it led to wave breaking, and it peaks around 3 to 5 days before the event. And that is what we see also, like this case I showed you for one large-scale event, around 3 to 5 days. So on 3 to 5 days, you see this wave breaking triggered by Central Asian high. So that is also consistent feature among other large-scale extreme rainfall events too. So once you have centralization high, one way it would help is like I had mentioned like monsoon trough. It comes in phase with monsoon trough, so it can intensify that. We can look at dynamic forcing. So this is magnitude of 2 vector here. So here it shows this nice extratropical tropical pattern. So monsoon lows can also add to dynamic forcing, but there is also this extratropical pattern which is patchy here. So it is hard to look out where is ascending and descending motion, because in general that's how the convergence of quantities are. They are patchy in field. But we can see, at least it shows that there is this nice tropical-extratropical interaction. There are also other ways how this centralization high would help. If we look at like wave activity flux, if it is converging in one sense, it indicates that there is wave breaking. In other sense, it would also show that monsoon trough, which has this cyclonic circulation or anticyclonic circulation, on its northern edge, it is easterly. So convergence of wave activity flux means it would accelerate easterly. So it would decelerate westerly flow, but it would accelerate like easterly flow. So that can strengthen this monsoon trough. I have plotted this geopotential height, stationary wave activity flux, and also so vectors here are stationary wave activity flux. These are rays traced using Rossby wave tracing, and these are geopotential height anomalies. So here this Rossby wave fluxes, so wave activity fluxes, they almost follow this Rossby ray paths also. So there is this component of wave activity flux that tends to follow the Rossby ray tracing. And same thing I had done at upper level, so it just like moves eastward along the chain. So summarizing a role of secondary cyclonic vortex. Here, large-scale extreme rainfall event, they are triggered in the western sector of monsoon low pressure system. They are assisted by the secondary cyclonic vortex, which are mainly present over western part of India. In between these two systems, there is large-scale convergence zone. It can lead to dynamic forcing at mid-level. Also, I had shown like metropospheric cyclonic vortex would help in organization of convection. There is additional dynamic forcing and also static instabilities. There is enhanced moisture flux because there is cyclonic circulation due to this. Also some indication of slowing down of low pressure system. So all these factors would contribute in triggering this large-scale extreme rainfall event. In terms of like understanding tropical-extratropical interaction, Atlantic blocking high is one interesting case over here. And also at upper level and mid level, there are these contrasting features which are like at mid-troposphere, there is direction towards the tropics for wave activity flux, which is not the case at upper level. But Atlantic blocking high can trigger this Rossby wave-like pattern, which strengthens this centralization high, which is important for wave breaking over this region during monsoon, and it can transport this PV streamers equatorward. At mid and low level, centralization high comes in phase with monsoon trough, so it can strengthen the monsoon trough and thereby synoptic systems embedded in that. So that's how I understand these tropical-extratropical interactions during summer monsoon. This video, I think on this laptop it doesn't play, but remind me to show that. So this particular event had occurred after the study period, but it had all those features that I just explained. But I can play it at the end of talk, and by then you can ask questions. So main question here, I had shown low pressure system is the main mechanism for all these extreme rainfall events. But then how do this low pressure system that triggers heavy rainfall events over central India differ from each other when they trigger like small, medium or large events? So that we see here. So this is plot for size of event. X-axis is size, y-axis is probability, and stars indicate probability of their association with low pressure systems. So earlier only I had shown most of them are associated with monsoon lows, and all these large events are associated with monsoon lows. This is so here I'm considering only those extreme rainfall events that were associated with monsoon lows, so that I can ask this question. This is rainfall distribution for small, medium and large event. Here we can see large event, they tend to be not only larger in spatial extent but also more intense. So these are different characteristics of low pressure system. So I have considered one more class of low pressure system that pass through central India but did not lead extreme rainfall. So that I call LPS or ES. And then other three classes, LPS that triggers small event, medium event or large event. CDF is cumulative distribution function, and these are three different characteristics like low level vorticity, speed of propagation, total column water vapor. Here we can see this low pressure system that did not lead any extreme. They tend to be weaker, they tend to be faster and also drier than other three classes of low pressure systems that trigger like extreme rainfall. Among these three classes, here I won't be showing all the characteristics, but in general we can see the dynamic characteristics like circulation related vorticity is different. Total column water vapor, it is not much different, so there is subtle differences, but if we look for like signal in different characteristics, like I'll show it here also. So low pressure system that trigger three different sizes, they tend to have like similar thermodynamic characteristics but different dynamic characteristics. So here I have plotted vertical velocity distribution for small, medium and large. The location of this plot, like center indicates location of extreme rainfall event. And here we can see small events, they tend to have like smaller ascending region, large event they have larger ascending region. So it seems to match maximum of pressure velocity and also its spatial extent. That is also kind of expected. Second column here shows relative humidity. So here it is now again with respect to these events, but like vertical profile, so it is pressure versus longitude. So here we can see the maxima in relative humidity. It doesn't really tell much about their spatial extent, but for medium and large event, it tends to have this strong saturated, deep saturated layer, which is not the case for small events. So for organization of convection, this is important to have like this deep saturated layer, so which you see for medium and large event. A couple of other quantities like flow level, potential, temperature, it tends to be similar for three different classes, but pressure, velocity or divergence, it is different for three different classes. So I can loosely say that thermodynamic characteristics are similar, but dynamic characteristics are different. And now further understanding what are differences between these three classes. So answer could be like in their spatial distribution. So I had earlier shown that like small events they occur mainly over western part and northern parts of central India. Medium and large they occur mainly over central India. And there was this study by Goswami and all. So they had looked at low pressure system data set during different phases of monsoon. So these are like intra-seasonal oscillation. 15 to 20 days time period they have, and during negative phase of meso or break phase of meso, monsoon low pressure system they are more towards northern parts, so near foothills and over western parts. During positive phase, monsoon trough is over central India, and monsoon low pressure system tend to go over central India. So here we can see some correspondence to the location of small events and low pressure system here, and for medium and large event. So like, okay, I thought maybe then low pressure system that form during positive phase of meso, maybe they'll lead to medium and large event, and those that form during break phase, they tend to give like smaller size event, and that turns out to be true. So I have also verified it using different things, but here I'll show you geopotential height anomalies at 500 HPA for small, medium and large event, 2 days before event and day 0. So here for small event, you see this anomaly is more positive over 7 peninsula, so it is typical break-like condition. And for medium and large event, so this is the monsoon trough I was talking about for large event. So there is this monsoon trough that is present for medium and large event, which is not the case for small event. So I can verify that using a lot of different things like rainfall anomalies over central India or vorticity. That all confirms that like this low pressure system that formed during positive phase tend to give larger event, and that formed during break phase they tend to give smaller size event. So there is a lot of dynamics behind that, but I don't have like sufficient time to cover all that, so I have just clubbed everything on this like flow chart here. So medium and large event they occur during positive monsoon intra-seasonal oscillation. So there is active monsoon trough. whenever there is active monsoon trough, there are enhanced meridional gradient of vorticity and temperature that can lead to large-scale dynamic forcing. Also, active monsoon condition means there is diabatic heating source at mid-troposphere. So once you have this mid-tropospheric diabatic heating source, that can generate potential vorticity at low levels and thereby strengthen low-level cyclonic circulation. So this idea actually I had gotten from actually John's book on TV. So that is inspired from that. And then I had also run vorticity budget for this low pressure system. So vorticity budget shows that whenever there is active monsoon trough, there is also strong low level shade. So that can lead to vortex stretching because it interacts with low pressure system and that can intensify these monsoon flows. In case of LPSLG, there is also a large-scale vertical advection. So that term also seems to be dominant, vertical advection term in vorticity budget. So that can intensify monsoon low pressure system. So this low pressure system that form during positive phase of monsoon intraseasonal oscillation, they tend to give medium and large event. On the other hand, low pressure system that form during negative phase of meso, they do not have active monsoon trough and they do not have this large scale dynamic forcing or diabatic generation of PV, or they do not intensify much. So these systems, they whenever they come over India, they lead to isolated thunderstorm and thereby small-scale extreme rainfall events. Also here I had shown like small, medium, and large event. They occur as a consequence of interaction between monsoon lows and also monsoon intraseasonal oscillation. So we can test that concept in terms of understanding their changes. So this is special plot for difference in the occurrence of small, medium and large event from the second half of study period to first half. So here we can see small events, they do not show like much pattern except that over northern parts it is actually decreasing, but over central India it is either increasing or decreasing. For medium you can see there is increase over central India. For large, because these events have occurred mainly recently after 1980s, so there is like this strong increase. So we can look at like mesoscale, this intraseasonal oscillation variability and synoptic variability during monsoon. So these are the regions where this variability has been increasing over central India, and that's where you see rise in medium and large event. On the other hand, small events which occur most frequently over here, this variance has been decreasing, and that's where smaller event they tend to show negative or no trend. So it follows that this hypothesis holds true even in explaining their observed trends. Also there is this study by U and team who have looked at like changes in tracks of low pressure system and extreme rainfall events. So low pressure system, they are in observation they are moving more southward over central India than the northern parts. And these are the regions where you see medium and large events. So you see increasing medium and large event but decreasing small event. For large event, I have briefly tested. So this study is kind of incomplete, but if somebody would want to take up, I would be happy to do that because I'm working on different things now. So this is like conditions for large event. So at 500 HPA, so I had looked at geopotential anomalies that are significant for this large event and looked at like pattern correlation. So y-axis here is days, x-axis is year. So here, if blue color indicates pattern was opposite to what is needed for large event, red color indicates pattern that is needed for large event, so similar to that. So in recent year, the overall circulation pattern it seems to be becoming more favorable for large event. More needs to be done, but there is like zeroth order understanding about like circulation also that is becoming more favorable for large event. So this is a summary. In first part I had shown that after 1990 it is size that explains the rising trend of extreme rainfall events, not the frequency of occurrence. I had divided extreme rainfall events into 3 different classes. Most of them are mainly associated with monsoon low pressure system, but at different large scale conditions. So this highlights the importance of definition of event. What we call an extreme rainfall event is important to understand their physics. Then I had explained mechanism for this large scale extreme rainfall event. So they are produced by interaction between low pressure system and secondary cyclonic vortex, and also extratropical forcing. So it shows like remote influences of synoptic-scale systems and tropical-extratropical interaction also for these events. So these events, they are triggered, so different spatial extent of heavy rainfall events have different preferences for monsoon interseasonal oscillation. So monsoon lows that form during positive phase of meso, they tend to be larger event. On the other hand, those formed during negative or neutral phase, they tend to be like smaller event because there is no active monsoon trough. Low pressure system that did not trigger extreme rainfall, they were deeper, faster and drier. So this highlights multi-scale interaction during monsoon that plays important role in determining the spatial characteristics of extreme rainfall events. And changes in extreme rainfall, I briefly showed that synoptic variability and interseasonal variability, it tends to match with the observed changes in medium and large events. So it is increasing over central India where these events show increase and decreasing over northern parts which shows decrease. And large scale conditions, they are becoming more favorable for large events. So this highlights these changing monsoon components. They could have influence on the frequency of occurrence of these large events. And this is brief summary. I'm happy to take questions, but then I'll just show you that video. Yeah, so this is event that occurred in 2017 over central India. There was flood. So this is relative vorticity at 500 HPA using ARFI data. So it is early data, and these are anomalies in relative vorticity at wind. Here, so I'll play it again. Sorry. So anyway, what this shows that there were two systems, low pressure system, secondary cyclonic vortex. It was also interacting with extratropics, so these vorticity filaments were coming from extratropics. And it had all the features that large scale extreme rainfall events would have, and it did lead to extreme rainfall event. So maybe I'll just stop here.
Thank you so much. We are out of time, so if you have questions, I'll just let you all maybe come up and ask. You will also be around, right? For
I'll be here for next 10 days.
yeah. Where are you at? So that everybody
On
knows.
15th floor, so
Okay.
mostly like Srinath's lab.
Okay.
Yeah,
Okay,
next
great.
up.
So please find her and chat with her while she's still here. She'll be around. So thank you so much again.
Thank you.